There are exoplanets out there that are fully oceanic. And out of those oceanic planets, some of them have floating water ice continents that can form in polar regions. If an oceanic planet has a great enough axial tilt, then that great axial tilt can create long and intense seasons. And if a year is long enough on such an exoplanet, during winter, in one of the hemispheres of the planet, at the poles, temperatures can drop way below freezing and cause for water there to start turning into ice on a massive scale. So essentially, on some planets out there, there are continent-sized icebergs. Then that huge iceberg can fully or partially melt during summer and then grow again during winter. And this can also occur at the other pole of the planet. Maybe on some of those planets, floating ice continents could even move around the ocean. Jupiter's moon Europa, for example, has a water ocean below its water ice crust, and the water ice crust has cycloidal cracks on the surface, which indicates that it moves independently of the ocean. So how do we know planets with these floating water ice continents can exist? Well, at least one reason is because we already know of at least one planet where floating water ice land forms. Earth is one of those planets. At the northernmost point on Earth, which is 90 degrees north, there isn't solid, rocky land. Instead, there is water ice that floats on liquid water. There is ice floating on water throughout the entire year in the Arctic. However, the amount of water ice over the ocean is at its lowest point during September. During that time, it covers a surface area of about 4 million kilometers square, and the water ice cover is at its greatest point typically in early March. During that time, it covers a surface area of about 15 million kilometers square. This map shows the Arctic sea ice thickness during winter. It reveals that the thickest part of the Arctic ice is more closely positioned to where the northernmost part of rocky land is present. So near Greenland and Canada, their sea ice thickness is 4 to 5 meters, and then going further away from that position, the sea ice thickness very gradually decreases. Rocky solid land to a large degree contributes to the formation of the Arctic sea ice, as it can cool down a lot more quickly and significantly compared to a large body of water. So sea ice can more easily form near rocky land. But with sufficiently low temperatures on certain exoplanets, water ice can form without any rocky land nearby. Antarctica also has sea ice that expands and contracts throughout the seasons. But beyond that, it also has huge ice shelves. They are essentially chunks of floating water ice that are consistently present throughout the years. It has them near land. Near Ross Ice Shelf of Antarctica, this image was taken. It is an insight into how the shores of floating ice continents could look like. Or maybe the shores could also look like this in certain places. This is an edge of an iceberg that detached from the Ross Ice Shelf. Besides water ice continents forming at the poles because of seasons, they could also form on fully oceanic exoplanets that are tidally locked. Tidally locked celestial objects are ones which need the same amount of time to rotate around themselves as they need to rotate around the object they are orbiting. Tidally locked planets are likely extremely common in the universe. One way that we can conclude that is because we know that red dwarf stars are the most common type of star. In the Milky Way, they are about 65% of the total number of stars. Red dwarfs are quite a bit smaller than the Sun, and the planets orbiting red dwarfs are also a lot closer to it. So most planets orbiting red dwarfs are tidally locked. So tidally locked oceanic exoplanets are very likely to exist. And because of that, on one side of them, it is always going to be day because it is always facing the host star. And on their other side, it is always going to be night. That is the side which is always facing away from the host star. On some of these tidally locked oceanic planets, the difference in temperature between the day and the night side will be such that on the night side there is a massive floating water ice continent. There is at least one planet which maybe has floating water ice continents. That is LHS 1140b. It has a diameter 1.7 times that of Earth, and a mass 5 times greater. Its density is just a bit too low for its size for it to be fully rocky, so it likely is still mostly rocky, but it also has either a bunch of atmospheric hydrogen and helium or a deep water ocean covering the entire surface. If there is a gigantic water ocean, then there is some chance for it to have floating ice continents. Although the equilibrium temperature of this planet is significantly below freezing, such is the case also for Earth, but the greenhouse gases can make it such that the overall temperature is well above freezing for this planet. So considering that just in the observable universe there are 2 trillion galaxies, the huge number of planets and moons in the observable universe implies that there are oceans that are made up of substances that are not water. Still, the floating ice continents are likely very uncommon on non-water oceans compared to water oceans, because unlike most other substances, water is more dense in a liquid than solid state. That's why water ice floats on liquid water. For most other substances, they are more dense in a solid compared to the liquid form. So because of that, we can predict that floating ice continents are at least much more rare on non-water oceans. Water oceans are likely the most common type of ocean out there. Water is made out of 2 atoms of hydrogen and 1 atom of oxygen. Now, hydrogen is by far the most common element in the universe, and oxygen is the 3rd most common element in the universe. In the solar system, the vast majority of major moons are at least around 50% water by volume, and round objects beyond Neptune are also in large part made out of water. For those objects, that water is mostly in the form of ice due to the extremely low temperatures present. However, on some of them, beneath their thick water ice crusts, there is liquid water that is shielded from the frigid temperatures. So the evidence for the abundance of water is clear. But when taking a look at the most common elements in the universe, we find that obviously hydrogen alone is much more common than water, which on top of hydrogen also has oxygen, which is a lot less common. Now, it is true that most of the reason hydrogen is so extremely common is because most stars are mostly hydrogen. But even excluding stars, hydrogen would still be extremely common in the universe, and that is because gas giants typically have immensely thick gas envelopes that consist mostly of hydrogen and a smaller part of helium. So considering how common hydrogen is, even on planets, there could be some rare scenarios where liquid hydrogen oceans form. There could be a planet out there that formed very closely to the host star, and it is mostly a rocky planet by volume. But it got just massive enough to start picking up hydrogen and helium that was once present in the protoplanetary disk, the 2 lightest elements. So this is a rocky planet that is much larger than Earth. Because of its strong gravity, it acquired an atmosphere several tens of times greater than the one on Earth. After this point, it then started going further and further away from the host star, eventually reaching a point so distant that temperatures dropped to about -250 degrees Celsius, causing nearly all of that atmospheric hydrogen to become a liquid, which left the surface with liquid hydrogen lakes, seas, or oceans. The atmosphere at that point is almost entirely made up of helium, because even at those frigid temperatures, helium would still be in a gas form. Potentially the same scenario could also play out with not just a giant rocky planet with a hydrogen and helium atmosphere, but also with a giant water ice planet with a hydrogen and helium atmosphere. Now, of course, one problem with such large planets which have strong enough gravities to trap hydrogen and helium is that they are also very likely going to be immensely geologically active, which could heat up the surface of the planet. But any heating from geological activity on the surface could easily be negated, provided that a planet is far away enough from the host star. Also, it is worth mentioning that, in a sense, Jupiter and Saturn do have hydrogen oceans. That is because at certain depths, the atmosphere has so much pressure that hydrogen and helium start having qualities of a liquid and gas together. However, the transition line between the semi-liquid and the gas atmosphere isn't exact. While in the previously mentioned scenario with a giant rocky or icy planet, the difference between the atmosphere and the liquid hydrogen would be a lot more obvious. Next, what about just oxygen, a component of water? Oxygen is the third most common element in the universe. At 1 bar, so the surface pressure on Earth, oxygen is in a liquid state between -218 and -183 degrees Celsius. Compared to many other potential liquids, this is a pretty wide temperature range over which oxygen can be a liquid, and as the pressure increases, oxygen can be a liquid over a much wider temperature range. At nearly 50 bars, it can be a liquid between -215 and -120 degrees Celsius. So there is a pretty good chance that there is some planet out there which has frigid, high-pressure nitrogen atmosphere which is cold enough such that nitrogen is still in a gas, but oxygen is in a liquid form. Liquid oxygen has a very apparent blue color. If the atmosphere is composed out of nitrogen without other things, then we can expect for a very blue ocean to be apparent on the surface of a planet with an oxygen ocean. So this would be a planet with a similar atmospheric composition to Earth and a much colder temperature. However, Earth got its massive quantity of oxygen through microorganisms performing photosynthesis. But for most planets out there with plenty of oxygen, we can expect that this is not how they got their oxygen. Potentially, oxygen seas could form on planets which are engulfed with a liquid water ocean and a water vapor atmosphere. We already know of quite a few potential exoplanet candidates with such characteristics. For example, Kepler 138d. Then the intense radiation from the close distance to the host star can lead to water vapor in the atmosphere to break apart and form various substances, among which some of them will be oxygen and hydrogen. Then such a planet can get very far away from the host star, causing for all of that surface liquid water and water vapor atmosphere to completely freeze. But in such a case, there could still be plenty of oxygen and hydrogen left in the atmosphere as they freeze at temperatures that are much colder. However, as the planet gets further and further away from the host star, some of that oxygen can then start to turn liquid and can even form oxygen lakes or even seas that sit on top of a water ice surface. We already know that liquid methane and ethane oceans are possible, since Saturn's moon Titan has huge hydrocarbon lakes. So oceans made out of carbon-based molecules are certainly possible. Carbon dioxide is definitely not uncommon. It is made up of oxygen, the third most common element, and carbon, the fourth most common element. In the solar system, both Venus and Mars have atmospheres that are about 98% just carbon dioxide. However, the atmosphere of Mars has only about 1% the surface pressure of the atmosphere of Earth, but the surface pressure on Venus is 92 times greater than the surface pressure on Earth. Venus also has a surface temperature of about 465 degrees Celsius, so it is far too high for CO2 to start turning into a liquid. Now, the atmosphere at the surface of Venus is indeed in a supercritical fluid state, so it has both properties of gas and liquid at the same time because of the immense pressure. But there is no clear dividing line between the atmosphere and the semi-liquid. However, if we took Venus and put it in orbit around the Sun at a distance much further away, the temperatures would begin to drop, and eventually at least huge, true liquid carbon dioxide lakes could start forming on Venus. This is a phase diagram of carbon dioxide. 1 bar is equal to the surface pressure on Earth. The phase diagram shows that at around 6 bars and above, then CO2 can start turning liquid, provided that the temperature is sufficiently low. So because the surface pressure on Venus is 92 bars, obviously it is capable of having actual CO2 lakes, at least. Also, this phase diagram tells us that Mars is incapable of having CO2 lakes. That is because its surface pressure is far too low. So on Mars, CO2 directly goes from a gas phase into solid phase as the temperatures drop. That's why during winter on Mars, at one of the poles, atmospheric CO2 partially solidifies, but CO2 lakes don't form anywhere on Mars. But what about just pure carbon, the fourth most common element? This phase diagram of carbon shows us that it is a liquid only under very extreme conditions, at pressures tens of thousands of bars and temperatures over 5,000 degrees Celsius. Interestingly, despite these extreme conditions, there is still one planet which maybe has a liquid carbon ocean. That is PSR J1719-1438b, a planet the size of Neptune that is about as massive as Jupiter. Its immense mass compared to its size tells us that it is extremely dense, and that likely it has plenty of highly compressed carbon, potentially diamonds, somewhere in the planet. Because there is a possibility that the surface of this planet has carbon and also an extremely thick atmosphere due to the immense surface gravity, and also extremely high temperatures due to its close distance to the host neutron star, that also means that a liquid carbon ocean might be present there. Besides carbon-based oceans, we can also expect for there to be planets with liquid nitrogen oceans. Titan has an atmosphere that is about 95% just nitrogen. Earth's atmosphere is about 80% just nitrogen. However, considering that the surface pressure on Titan is 1.5 bars, so similar to Earth, and considering that the surface temperature is minus 180 degrees Celsius, it is just a bit too hot for liquid nitrogen even there. However, it is very much possible that Titan was a bit colder in the past, and that it had enough pressure such that huge liquid nitrogen lakes were present on its surface. So nitrogen seas and oceans are very likely to exist somewhere in the universe. Potentially, there are also oceans made out of nitrogen-based molecules, or at least lakes. One such nitrogen-based molecule could be nitrogen dioxide, which naturally occurs on Earth through lightning. So because lightning is one source of nitrogen dioxide, there could be a planet out there with a similar atmospheric composition to Earth that has a thick cloud cover over the vast majority of the surface. With that, it could have also much more lightning and produce a lot more nitrogen dioxide, enough for lakes entirely made out of it to be present somewhere on the surface. The sixth most common element is iron. Iron oceans likely do exist, at least to an extent, as typically the iron found on Earth is in an oxide form, so not pure iron. So planets that are very hot could have iron oxide oceans. As to whether or not there are planets coated with just pure iron such that they can turn liquid is very hard to say. Same is true for 8th and 9th most common element, which is silicon and magnesium. They typically aren't found in a pure form on Earth, so it's very hard to say as to whether or not pure silicon or magnesium oceans can't exist on some planets, and even if they do, they aren't all that exciting as they would be devoid of alien life due to the devastating temperatures. The chemistry of such oceans simply wouldn't allow for the formation of complex molecular structures which are necessary for life. The 10th most common element is sulfur. Elemental sulfur is present on Earth in volcanically active regions. Venus has sulfur in the form of sulfuric acid clouds that contribute to the surface of Venus not being visible from space. It also has a small part of sulfur dioxide in the atmosphere. Mars also has a small percentage of the atmosphere in sulfur dioxide form. But elemental sulfur was also found on Mars by the Perseverance rover in June of 2024. However, the place in the solar system with the greatest amount of sulfur on the surface is Jupiter's moon Io. Its surface is coated with sulfur and sulfur dioxide. It also has an extremely thin atmosphere composed out of sulfur dioxide. It is present due to the immense volcanic activity. If Io had a significant atmosphere of 1 bar, for example out of nitrogen, then if the surface temperature were quite a bit higher, that is around minus 40 degrees Celsius, then all of that sulfur dioxide on the surface of Io would turn into a liquid which would likely create at least lakes. It's easy to imagine then that there could be a planet or a moon out there with the right conditions for at least sulfur dioxide seas. So those would be intensely volcanically active planets that through volcanoes spew sulfur that is present in the deeper layers of the planet. But despite the volcanic activity, due to the great distance from the host star, the planet could be overall very cold in places and time intervals where there isn't volcanic activity, at least cold enough for huge sulfur dioxide seas to form. But what about just pure sulfur? Well, those could exist on planets similar to Io, but the temperature necessary for pure sulfur oceans would have to be pretty high, as sulfur at 1 bar melts at 115 degrees Celsius. It also boils at 444 degrees Celsius, so there is a very large temperature window in which liquid sulfur can exist, which is actually good news for the existence of sulfur oceans. There could also be ammonia lakes or oceans, chlorine lakes or oceans, or combinations of two different substances in a liquid form, such as methane and ethane on Titan, or 3 or 4 different substances. There is an enormous amount of different possible types of liquids that can technically create oceans. Of course, out of the total number of elements and molecules which can technically create oceans, likely only a small part of those liquids can realistically naturally form on planets. When it comes to just elements alone, every single one has a gas, solid, and liquid state. And a lot of the molecules which are made up of those elements also have liquid states. So even if most liquids can't naturally form on planets, that still leaves us with plenty of variety.